learn like a pro.
Got a chemistry exam breathing down your neck? Don't worry. We're going to get straight to the point and absolutely nail one of the biggest concepts you need to know: isotopes. Let's break this down so it makes perfect sense.
Okay, so let me ask you something right off the bat. Is it possible for two atoms of the exact same element, let's say 2 atoms of chlorine, to actually have different masses? I mean, it sounds kind of weird, right? But the answer is a big, resounding yes.
And that is where isotopes come into play. Now, this right here is the definition you need to burn into your memory. Isotopes are atoms of the same element. That means they have the exact same number of protons. You can think of the proton number as an element's unchangeable ID card. But, and this is the key part, they have a different number of neutrons packed into their nucleus. Same protons, different neutrons. That's the whole story.
So, if we're changing the number of neutrons, it's pretty obvious that's going to affect the total weight of the atom's core, right? And we have a name for that total count, the nucleon number. It's super simple. Just add the protons and the neutrons together. You'll also see this called the mass number on your test. They mean the exact same thing, so don't let the two names throw you off.
Okay, let's look at this in action with a real example. This table makes it crystal clear. We've got 2 common isotopes of chlorine, chlorine-35 and chlorine-37. First, just look at what's the same. Protons, 17 for both. That's what makes them chlorine. Electrons, 17 each, keeping them neutral. But now, look at the neutrons. This is the difference maker. Chlorine-35 has 18, but chlorine-37 has 20. 2 extra neutrons. And when you do the math, you see the result. For chlorine-35, 17 protons plus 18 neutrons gives you a nucleon number of 35. For chlorine-37, it's 17 plus 20, which gives you 37. See? Same element, different mass.
All right, so this leads to the next big question you're probably going to see on your exam. If their masses are different, do isotopes act differently when it comes to chemical reactions?
The answer to that question comes from one of the golden rules of chemistry: an atom's chemical personality. You know, how it bonds, what it reacts with, its entire behavior is all decided by its electrons, especially those electrons in the outermost shell. So, let's connect the dots. Since all isotopes of an element have the same number of protons, they also have to have the same number of electrons to stay electrically neutral. The neutrons, they're just chilling in the nucleus, adding a little weight. They don't affect that electron party happening on the outside one bit.
And this slide right here, this is your ultimate takeaway. This is what you need to know. Because they have the same number of electrons, isotopes have basically identical chemical properties. They'll form the same bonds and react in the same ways. But because they have a different number of neutrons, their mass is different. And that means their physical properties, stuff like their density or boiling point, can be slightly different.
Okay, let's lock this all in with a quick final summary. This is your exam cheat sheet. On one side, what's the same? The number of protons, the number of electrons, and therefore their chemical properties. On the other side, what's different? The number of neutrons, which changes the total mass number, and that leads to different physical properties. If you can remember that, same chemistry, different physics, you've got this.
So I'll just leave you with this final thought. If their chemistry is almost exactly the same, where could that tiny physical difference in mass actually be important in the real world? Well, it turns out it's a huge deal. That little bit of extra weight is the principle behind everything from carbon dating ancient fossils to life-saving medical imaging. So yeah, that tiny little difference in mass, it has massive implications for our world.